and welcome to our next session here in our boosting chapter. Today we'll talk about component-wise boosting, which is also sometimes called model-based boosting. I guess that's a more, I don't know, not sure whether I want to say that, statistically flavored version of gradient boosting, where we will use somewhat simpler base learners, usually linear effects or spline-based learners, to model univariate features. And it's a kind of a nice idea to combine the loss minimization pseudo-residual principle of gradient boosting with semi-parametric models from more statistically flavored learning approaches. And I guess in the end, hopefully you can see that this gives rise to a model where you can kind of drive down an arbitrary loss function, but the resulting model will have built-in feature selection, and depending on which base learners you use, you can also get produce something like a GAM model, so a general additive model, and you get something like marginal effects, so partial dependence curves and so on in a certain sense for free. I guess all of that will become a bit clearer after we have moved through the basics, so I guess let's start doing that. So as we've already learned here in this chapter, gradient boosting with trees is quite a strong predictor. It's quite strong predictive performance, and that's kind of a combination of this non-parametric property of the trees and also this aggressive risk minimization that we get from the gradient boosting principle through this gradient descent in function space that we're performing in gradient boosting in general. We discussed that at length. Usually, I guess, well, not always, but very often our example has been gradient boosting with trees, and we had some specific sessions also on that, how to kind of exploit the tree structure in gradient boosting. And we also discussed that the resulting model, so gradient boosting with trees, can even be, to a certain extent, quite interpretable if we're just using stumps, because then we are still fitting such a GAM model. And you again get these partial dependence curves and marginal effects for free. You can do this also maybe with trees of depth 2. Then you have already these two-way interactions in there. The model becomes less interpretable, but if you have considerably larger trees in there, the resulting ensemble is not very interpretable anymore. Here we will basically, I guess, keep nearly everything of that general gradient boosting template, but we will select a specific class of base learners, or we will kind of now work with a pool of different base learners and hopefully through that construct a more interpretable model. So the idea is kind of to keep nearly everything in there that gives rise to pretty strong predictive performance, to still work with interpretable components. We'll also see that at the end, because of this approach, we basically get an automatic selection of components and features. So you can have components gradient boosting be set up in a way that you really do direct feature selection, or maybe you have a different pool of base learners where you're not sure which of them make the most sense, and then gradient or component-wise boosting will also select from these. And at the end, you get hopefully a quite sparse model that you can interpret quite nicely, where you can discuss which features make the most sense for the data at hand, which base learners make the most sense for the data at hand, and so on. And some people call this component-wise boosting, and other people call this model-based boosting. There are now a couple of implementations available in R to do that, but let's, I guess, start with the basics. So what we will now here do is we will generalize this concept of having basically one class of base learners. So I don't know, some regression trees, maybe up to a certain depth of, I don't know, 2, 3, or 4. We'll now generalize this to a pool of base learners. So what do I mean with pool of base learners? So there will be a set now. Again, my pen tool doesn't work, so there will be a set of these base learners. And each with associated parameter spaces, and in each boosting iteration, we will figure out the best from each of these hypothesis spaces, capital B1 to capital Bj, compare them with respect to their SSE, how well they fit against our vector of pseudo-residuals, and then just take the best of these, okay? So we'll have kind of an extra inner loop where we fit against each of these candidate pools, each of these candidate sets of models, and then just take the best overall. So what we are usually going to do, and that also kind of gives rise to this implicit feature selection effect, is that we will now have these pools, or these hypothesis spaces associated with individual features. And I guess that's, I mean, we're not always doing that. We can also use that to model interaction effects. We can use spatial effects or temporal effects. I can make that much more general and complicated, but if you want to have like a simple and also pretty relevant and practical thing in mind, think there's now a pool of base learners, there's one base learner, so to speak, associated with feature 1, there's one associated with feature 2, feature 3, and so on. So what we could, for example, do, and we can even have like different functional forms now associated with different features. So a simple base learner, configurable base learner for a feature could be a linear effect. We could also say we are using a nonlinear spline effect for a feature. We can even have the algorithm select from these different functional forms. We can use a dummy encoded linear model to model categorical features, or we can use, like I said, more complicated stuff like, I don't know, tensor product splines for interaction modeling. We can do spatial effects. We can use Markov random fields. Let's keep it simple here. So think simple functional form, so linear effect or spline defined on an individual single feature. So one thing we'll also exploit here is that all of these base learners are usually additive in their structure. So for linear effects and for splines, all of this holds. So what do we mean with additive structure? So we mean that if we add two of these base learners together and we look at the resulting function, so and here I mean two concrete parameterized base learners with a parameterization θ1 and θ2, what we can also do is we can just add up their parameter vectors directly and parameterize our base learner with the sum of these two parameter vectors, and that's exactly the same as adding up the two functions. And I guess that's what we mean if we say linear model, right? So linear model means it's linear in the parameters, and you know that splines and so on are linear in these parameters, and that is why we do like them quite a lot in traditional statistical modeling, because then we can exploit and reuse all of this machinery for linear models. Use the normal equations and so on. Now, I guess that's probably the most important slide here in this first basic session. This is now how our component-wise boosting algorithm looks like in pseudocode. Okay, it's pretty lengthy, a lot of formulas going on, a lot of symbols and so on. But good news is we have not really changed a lot. So initialization is the same. We just initialize with a constant. There's now like our usual loop here of boosting iterations. So yeah, we boost in components a couple of times, I guess a capital M times. And then in the first step in each iteration, we compute this vector of pseudo-residuals with reference to our loss function of choice that we have selected to kind of boost against. And now what we would usually do here, instead of this blue part, and that's the only thing that has changed, we would now fit our base learner, our one base learner, which is a parameterized function, just kind of simple machine learning algorithm, our weak learner, against our vector of pseudo-residuals with respect to the L2 loss. So normal gradient boosting would just run this line here, right? And then add that fitted model into the mix here. Now, in component-wise boosting, it's a little bit more difficult, but not a lot. So the only thing we are changing is that we have here our pool of multiple parameterized base learners. So all of these are different parameterized functions now. And again, very often, the first parameterized function only refers to feature 1, only acts on feature 1, the second only on feature 2, and so on. And we now just do exactly the same as I've described before, but for each individual base learner. So we fit it against our vector of pseudo-residuals, and that gives rise to a kind of the best parameterized version of that base learner. So we get our hands on the optimal parameterization. We put that away into memory, into a little table, but we also store the SSE that we get for that specific parameterization. And then we do that again for capital B2, for capital B3, and so on, until we have like swept through that complete pool here. And at the end, we just look at our table of optimal parameterizations and their associated SSE values, and just pick the best one, okay? Just pick the best and add that into the mix. And all of the other guys, the, I don't know, J-1 other suboptimal candidates, we'll just ignore in this iteration. And then we'll do exactly the same again. Yeah? Again, compute our vector of pseudo-residuals. We iterate through all of these J-base learners. Pick the one which is SSE minimal in its fit against the pseudo-residuals, add it into the mix, and so on, and so on, and so on, and so on. Now, I guess maybe it's a good idea to look at an example. So we did that here. So we now, I guess you now have to focus so mainly on the bottom part here. So at the top, you see just a copy-paste version of this inner loop from our algorithm. And let's go through this so we can really understand this. So we are in a certain iteration M. We have our data, we have our vector of pseudo-residuals, and we now fit. And we have now, exactly as I've described before, we have one base learner per feature. Here we have 3 features, so there are 3 potential base learners that we can pick from. And we are also using something like a spline here. And we now fit against x1, and we store the SSE. And you see here this little function, right? Fit it against the pseudo-residuals. And we do that for our x2, and I would add in such a little function here, and you can see, well, that SSE is apparently a bit worse, so we're not going to select that at the end. And now we try out our third feature, and you see that this will give an SSE when fitted against the pseudo-residuals, which is a bit better than the last one, but still not beating what we got from the first feature. So we'll add in this guy, okay? And I guess now you can also see where the feature selection comes from, right? Because we're now adding in an effect that refers to feature 1, but we have not added in anything yet that refers to feature 2 or 3. So, and this is why we say that this gives kind of rise to, I guess we could say, a nicely integrated or embedded feature selection, as long as we define these base learners on individual features. Yeah, I guess what is also important to say is that because we are not like removing a certain base learner from the pool after an iteration, so it can be selected again and again and again and again in upcoming iterations. The effect of a single feature can be changed during the individual boosting iterations. So you might run, I don't know, 50 iterations of component-wise boosting, but you're touching and adding in always an effect referring to the first feature. So that depends on whether you get more information by like strengthening the effect of a certain feature or adapting it or adding in a different one. And also don't forget, we have this step size parameter in there that kind of dampens the effect of an individual base learner. We talked about this when we talked about regularization. And especially also because of that, it can very likely happen that if you're touching a certain feature in a certain iteration with a very minor step size, you're going to do it again and again and again a couple of times, and then maybe after that a different feature is selected, and then maybe we're back to the first and so on. But at the end, what you can do is if you look at all of your added effects in each iteration, you can kind of group the ones together that refers to a single feature, and hope also that refers to the same base learner class. So let's assume at the moment there's maybe only one, right? But as we said before, these models should be additive. So you can kind of just group them together and just add up all of the parameter values, and then you get one function for this one feature. And if you have multiple functions acting on the same feature, you have to group together the parameters that refer to that one feature for that one specific base learner type. Okay, but again, then you can add everything up, you get one nice parameterization, and if this is univariate, you could even plot that, and you get your partial dependence plot for free. We'll discuss that a bit later in an upcoming session.